welcome again. We are studying the second part of this course, which is on electronic instruments. And as a background, we have started studying some discussion on basic electronics. So in the last class, we have studied starting from SR flip-flop, then we have studied D flip-flop, then after that we have studied two variants of D flip-flop, level triggered and edge triggered. Okay. So, and then we have seen a circuit called master slave circuit for an edge triggered D flip-flop. So, after that today let us take another flip-flop which will be very useful for further studies. It is called T flip-flop, T for toggle, or T flip-flop. What does it do? So, let us see first the function, then we will see the circuit. So, functionally it has one input T, T for toggle, and one output Q. Now, the function or the rule is that if T is equal to 0, so it has only one input, so that input can be either 0 or 1. So, this is the input side, this is the output side. So, if T is equal to 0, then Q will remain at its value, whatever the value is. If the Q is now at this moment 0, then Q will remain at 0. If Q is 1, then it will remain at 1. So, I can write Q next. Next means at the next instant, this will be equal to Q previous. That means the value of the Q at the previous instant. Okay. So, and if T is equal to 1, then Q next will become Q previous bar complement, opposite of Q previous. So, if T is set to 1, if the input is 1, and now at this moment Q is at 0, then at the next moment Q will become 1, and then again at the next moment it will become 0. So, it will toggle. Toggle means it will change, alter. Okay. So, this is the rule. Now, there is a small observation. So, in this case, observe when T is equal to 1, then Q will, that means the output will continuously change, continuously oscillate, change or toggle. Okay. So, if T is equal to 1, then Q will become from 0 to 1, then 1 to 0, and so on. It will keep happening very fast, continuously, like this. Okay. So, this type of T flip-flop is therefore not very useful. So, we need a small modification which will become useful. Okay. So, the modification is this. This is the T flip-flop. It has input T, output Q. We will have a clock enable En. Okay. So these are inputs, of course, and this is the output. Now, this symbol, this triangle, as I told you before, represents a edge triggered input, particularly positive edge triggered input, because there is no bubble before this. So, this is positive edge triggered. So now how will this device work? So the rule is that if t is equal to 0 at the moment when a rising edge, so let me draw it like this. So this symbol means a rising edge. For ease of writing, I'm using it. So when a rising edge comes at enable, if t equal to 0 at the moment when this rising edge comes at enable, then q will remain unchanged, but if or else if t is equal to 1 at the moment when this rising edge comes at enable, then q will change. So what does it mean? So it means, say if I draw some timing diagram like this, let this be time, then this is let this be the toggle t, okay, and say t is varying like this. So it is initially 0 from here to here, and then say it becomes 1 from here to here. So this is t. And if I have this enable like this, say 0 1 0 1, so this is how it is changing. Then how will be the q output? So let's see that. So this is the q. Now let's assume that q is initially 0. Okay, you can also assume that q is initially 1. So whatever you like, you assume. So say I'm assuming that q is initially 0. So here at this moment it is 0. So assuming q equal to 0 initially, okay, so then at this moment it is 0. Now you see toggle is 0 from here to here, so nothing will happen because toggle is 0. No matter whether rising edge, falling edge, whatever comes at enable, nothing will happen to q. Q will remain unchanged. So from here to here, so that means up to this point, nothing happens. Q is exactly equal to 0 always. Okay. Now after that, toggle is 1. So now q can change. When can it change? Only if there is a rising edge at the enable. So it is here. Okay, so observe there is a rising edge here. This is not the rising edge, this is a falling edge. Then another rising edge is here. So these are the instants where q can change because t is 1. So at this moment, that means here q will change, will go from 0 to 1, and then here again it will change. It will go from 1 to 0. It will not change anywhere else. Then it will remain 0 until another rising edge comes. At the same time, t should also be 1. So that's the rule. For q to change, for output to change, we need the toggle to have the value 1, and a rising edge should come at the enable pin. Okay, so this is the positive edge triggered T flip flop. Okay, and this T flip flop, this is useless. I hopefully useless, I guess. I don't know whether this can be used. Okay, so this is the T flip-flop. Now, okay, so similarly we can have another T flip-flop, another type of T flip-flop, which is negative edge trigger T flip-flop, whose symbol will be just like this. We will have a bubble before the enable. This is T, this is Q, input output. So this is negative edge triggered T flip-flop. Okay, now let us see how we can make this flip-flop. Okay, so we know how it functions, how it works. Now let us see the circuit, or how we can make it. So we will make it using a D flip-flop. Okay, so if you recall, we first studied SR flip-flop. Then with SR flip-flop we made a D flip-flop. Then with D flip-flop we made a edge trigger D flip-flop. And now we'll make a edge trigger T flip-flop using a edge triggered D flip-flop. Okay, so we will have this edge triggered D flip-flop. So let me first draw the D flip-flop. So this is D, this is output Q, and it has a enable, call it En. It can be positive edge triggered or negative edge triggered, whatever you like. If I say take a negative edge triggered, I can take it, no problem. So this is a D flip-flop, edge triggered of course. Now using this I will make a T flip-flop. How? Let's see. Okay, so for that you just observe this rule or truth table. Okay, so if now the input is T, output is Q, or call it Q next, means at the next moment after the clock pulse or clock edge comes at enable. Okay, so this is input, this is output. Now if T equal to 0, output will be same as Q previous. Okay, so let me also write Q previous. Okay, so if Q previous is 0, out Q next will also be 0. And if Q previous is 1, Q next will also be 1. Then, but if T is equal to 1, then I have two choices. If Q previous is 0, Q next will become 1. If Q previous is 1, Q next will become 0. Now you see that this truth table is the truth table of a XOR function. So we can write that Q next, this is nothing but, okay, this is Q, this is T XOR Q previous, which you can also write T Q previous bar or T bar Q previous. Right? So when they are unequal, then the output becomes 1. If they are equal, 0, 0 or 1, 1, output is equal to 0. So what we do, we do it like this. We take a kind of feedback. Then here we use a XOR gate. This is XOR gate, and here it has two inputs, one which is coming from Q, or you call this Q previous, and this is T. and this entire thing is the T flip-flop with negative edge triggering. So this is enable, okay, and this is T flip-flop, negative edge triggered, negative edge triggered. Okay, let me take you outside. Okay, so this is the circuit of this symbol. Okay, so that's so simple. Now we have studied T flip-flop, so now we will make first more interesting circuit, which is of a counter. Okay, so we will now study counter, and this is called a binary ripple counter. So we will make it using T flip-flops. Okay, so let us see how. Say I take a couple of T flip-flops. Let me take a few. 1, 2, 3 and 4. So these are all T flip-flops, and so they will have input and output. So let me draw the input on the right side and the output on the left side. Okay, I'm doing it on purpose. There is a small reason, and there is no harm in drawing the input on the right side and output on the left side. Although in general we do it opposite, but here I am doing it on purpose. Okay, so this is Q output, T input. So it will have another input, enable. Let me use edge triggering and negative edge triggering. So this is enable. So all these T flip-flops are like that only. Okay, and let's call them, let's give some names, flip-flop 1, 2, 3, 4 or whatever. So let's call it flip-flop, let's call it 0, flip-flop 1, flip-flop 2, flip-flop 3. I am counting from right to left. Again, there is no harm in doing that. You can also count from left to right. Okay, so then you can call this Q0, T0, Q1, T1, Q2, T2, Q3, T3, enable 3, enable 2, enable 1 and enable 0. Now what I will do, I will say take a clock generator. Okay, so let's take a clock generator. It can be a crystal oscillator or whatever it is. What is a clock generator? It generates a square wave continuously. Okay, so this is its output. So clock generator generates clock signal continuously with same period or same frequency. And what I will do, I will connect this output here. So that means I have this clock signal square wave coming to this enable continuously. And then what I will do is this, I will connect this T0 to voltage level 1. Okay, so this is the symbol for logic 1. So let me write it here, symbol. So you know that this symbol means ground or earth or zero potential. So often we also draw it like this. Okay, so this is, and in case of digital circuits, this is like low. This represents logical low. Similarly, logic high can be represented with this symbol. Okay, with a bar like this. So this is the symbol for logic high. Okay, so this is connected to logic high or 1. So this is 1 continuously. Okay, right? So this is continuously 1. Similarly, this also I will connect to logic 1. This also to logic 1. These are all connected to logic 1 permanently. So these toggles are on always. Now what happens? This clock pulse is coming. So let's call this signal as CLK clock. Okay, so now let's draw some timing diagram. This is time versus clock CLK. Okay, and this is like this 0 1 okay, this is like this. It may be of uniform frequency, but my drawing is not. Okay, then how will this Q0 output change? Let's find that out. So Q0, how will Q0 behave? Time versus Q0. This is the output of flip-flop 0. So say initially, assume initially Q0 equal to 0. Okay, so say at this point this is 0. So assuming Q0 equal to 0 initially. So at this point this is 0. Okay, then it will change. When will it change? It will change at the next negative edge, right? So where is the next negative edge? So the next negative edge is here. So then this Q0 will change from 0 to 1 here. Okay, because this T is always 1. That means whenever a negative edge comes, falling edge comes, this will change. Q0 will change. Then where is the next negative edge? Next negative edge is here. Similarly here, 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 and so on. Right? Now that means Q0 will change after this at this point here. So it will change here. We'll go from 1 to 0, then like this. Okay. So now let me ask you a small question. So the question is, suppose the frequency of this clock signal is frequency is equal to say f. Then what is the frequency of Q0? You see, it is half of this frequency, f by 2. Okay, so because every every alternative pulses, all these negative pulses, positive pulses do not work. These alternative pulses, they change q0, right? Okay, so every alternative pulses, this negative pulses, they change q0. So if this is changing with a frequency f, then this is changing with a frequency f by 2. I can also write that the time period, if this time period is t, which is 1 by f, then here time period is how much? 2t, right? Now what I will do, next thing is this, I will connect this q0 to this enable. Okay, so this is the important thing to observe. Okay, so now this q0 is also, this is also a square wave changing at some frequency, half of the frequency of this one, right? So instead of connecting a clock, I can connect q0 here. So this will also behave like a clock, right? So okay, so then this q1 will change. Now how will this q1 change? Let's see how will this q1 change. q1 versus time. Again, assuming q1 is equal to 0 initially. Okay, because we have to start from somewhere. If we do not know the initial value, we cannot proceed. So let's assume it is initially 0. Then it will change. When will it change? It will change when there is a negative pulse here. That means at q0. So the negative pulses are here, 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 here. So q1 will change here from 0 to 1, then here from 1 to 0, then here, here, and so on. So now you observe what? That the frequency here is f by half of this, f by 4, and time period here is 40, double. Okay, so this is how q1 behaves. Now what I will do next, you can guess easily, is that I will connect this q1 to the enable of flip-flop 2, and similarly I will connect this q2 to the enable of flip-flop 3. So then what will happen? So this you can do it yourself now. So let me draw time versus q2. Again, let's assume that it starts initially with value 0. Okay, then it will change. When will it change? It will change here and then here. So then q2 is up to this, this is 0. Then here it will become 1, and then here it will become 0, and so on. So that was q2. Now q3, how will it be? Time versus q3. So q3 will change when there is a falling edge here. So that means up to this moment, from here to here, this will remain 0. Then it will go to 1 and will remain at 1. Okay, once again we are assuming that initial value of q3 is equal to 0. I'm not writing because I do not have space. And here the frequency, okay, what is the frequency? Frequency is f by 8, time period is 8t. Okay, here for this q3 frequency is f by 16, time period is 16t. So time period increases from t to 2t, 4t, 8t, 16t. Frequency decreases f to half f, 1/4 f, f by 8, f by 16. So this is how this Q0, 1, 2 and 3 will change. Now let me do this. Let me take this Q0, 1, 2, 3 as outputs. So let me take this 1, 2, 3 and 4 as outputs, and let me seal everything here inside a box. So this everything inside the box is my counter, and these are the 4 outputs. Okay, Q0, Q1, Q2, Q3, and so these are the outputs, and this clock here. So this is the input of this box, which I call a counter. So this I will call a ripple counter. It's written here. Why do I call it counter? That's the important thing. Okay, so for that, let us observe. Let me go to the next page. Let me have just this timing diagram in front, and let me write the value of this Q3, Q2, Q1 and Q0 as a function of time. Okay, so this way time increases. So initially you see all the values are 0, 0, 0, 0, 0. Okay, forget clock, 0, 0, 0, 0. So everything is 0, 0, 0, 0. Now after that, when this first clock pulse comes, okay, after this first clock pulse, here you see the values are 1, 0, 0, 0. So at the next moment the values are Q0 is 1, everything else is 0. Now what happens after this next clock pulse? So after this boundary, okay, here you see this is 0, 1, 0, 0, 0, 1, 0, 0. After that, let's see here after this clock pulse. So that means after this line, okay. After this we have this is equal to 1, 1, 0, 0, 1, 1, 0, 0, and this is how the Q0, 1, 2 and 3 is changing with time after each clock pulse. Okay, so now you see this number 0, 0, 0, 0 is same as binary 0. This number 0, 0, 0, 1, this is same as binary 1. Okay, this is 0, 0, 1, 0 is same as binary 2. This number 0, 0, 1, 1 is same as binary 3. So this 4 voltages, or this Q0, 1, 2, 3, they are counting the binary number 0, 1, 2, 3 and so on. Okay, if you follow this pattern over time, say if let's take another instant. So after this clock, okay, so after this clock the value is say 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. This is nothing but binary 4. So this way this counting is going on. So that means this circuit is counting the number of clock pulses coming here, because every time a negative clock pulse or a falling edge comes here, the binary value or binary equivalent of these 4 numbers q0, q1, q2, q3 is incremented by 1. Okay, so every time a edge comes, falling edge comes here, these 4 numbers, these 4 bits, you can call them bits, they increase by a value of 1. So this, here you observe, this circuit is counting the number of falling edges. Okay, falling edges means like this, coming at the coming from at this point input. Okay, call this clock, coming at clock CL. Okay, so this circuit is counting the number of pulses that come here. So that's why we call it a counter, right? And why do we call it binary counter? Why binary? Because these 4 bits are counting in the form of binary. Okay, so this 4 q0, q1, 2, 3, they represent the value 0, 1, 2, 3, etc. In binary form. So we call it binary counter. And why do we call it a ripple counter? This is possibly because all this, I mean, I do not know exactly why, but I guess because this q0, q1, q2, q3, they are all oscillating. Okay, they are going up and down like a ripple. Or you can also think that this input also have ripples, they are going up and down, and it is counting the number of ripples or number of oscillations. Okay, so that's why possibly it's called binary ripple counter. And here this we will call the LSB, least significant bit, right? And this is, you know, is the MSB, most significant bit of this counter. Okay, now some small questions which you should answer right now. Question: so the above counter, how long can it count, or how far can it count? How far or long can the above counter count? Do you have the answer? The answer is up to 15, decimal 15, or binary. So which is, so this is in decimal, or in binary this means 1111 in binary. Okay, so after this what will happen? After that everything will become 0 again. So this is called a modulo 16 counter. Why 16? Because it counts 16 numbers starting from 0 to 15. Okay, so there are 16 numbers including 0. So 0 to 15 there are 16 numbers, so we call it a modulo 16 counter. Okay, so now let's see another important circuit which will be very useful, is a decimal counter or a decade counter. We also call decade counter. You can also call this decimal counter. Decade counter is the actual name. But I mean, for your understanding, you can call it decimal counter. You can also, and this is also same as modulo 10 counter. Okay, so what is this? So this will count. So it will count from this will counts from 0, then 1, 2, 3, so on up to 9, 8, 9, and after that it will become again 0, 1, 2, and so on. This is how this will work. Okay, so how can we make that? Let's see. So we will just use the previous binary REPL counter, and we will use this idea but make some modifications to make this decade counter. Decade means 10. Decimal also means 10. Okay, so and we can make it in different ways. I will show you a way which I think is easy. That's why I will show you that. But for that we will need this. We need a T flip-flop with reset input. Okay, so what is this? So this is a T flip-flop. So a T flip-flop, as you already know, has input T. It has clock enable. I'm taking a negative edge triggered T flip-flop. This is the output. So this is the normal T flip-flop. But now what we are going to use, a modified one which will have another input, call it reset. So it has 3 inputs, 1 output. This is a new one. What is the function of reset? Q will become 0. Okay, immediately when reset is equal to 1. But when otherwise, when reset is equal to 0, this will behave like an ordinary T flip-flop. This will behave like a normal T flip-flop. Okay, that means if this is 0, then Q will change if T is equal to 1 at the moment when a negative edge comes here at enable. Okay, but this reset is a new input which will make the output equal to 0 no matter what the previous value was. If it was 0, then also it will become 0, and if it is 1, then also it will become 0. So no matter what the previous value is, output will become immediately 0. Immediately means so it will not even wait for the clock. So it will not even wait for the clock. So this is what we want. This is the behavior of this flip-flop. That is what we want. Okay. Now how to make it? What should be the internal circuit? Can I keep it that as a small exercise? You try it yourself. That will be fun. Okay. So homework. Try to find the circuit which will realize this behavior. Circuit realization. Okay, try this. It will be fun. But this is what we want. We want this T flip-flop to behave in this way. Now, if we have this T flip-flop, then what we will do is this. We will use this structure, same structure. Copy, paste. Okay, so now we are going to make a decade counter. So So what we will do, we will use T flip-flops which has the reset function also. Okay, so it will have another input. Where do I write? Let me erase this and let me write the reset here. Okay, because I do not have space here, so let me write reset here. So this is the reset input. Similarly, this is the reset input, this is the reset input. So this is input, right? This is not out. Okay, so I have no space to draw here, so I'm drawing it here. So this is R. Okay, so I have 4 reset inputs, and what I will do, I will connect these all reset inputs together. I'll sort them, and now what I will do is this. So I know this this is Q0. So I know this Q3, Q2, Q1, Q0, they vary with the input pulses like this, starting from 0, 0, 0, 0, okay, then 0, 0, 0, 1. This is how a normal binary counter behaves, then 0, 0, 1, 0, so on. So this is like decimal 0, 1, 2, and then after a while this will become 8. 8 means so 0, 1, so 8 is this. Okay, so this is 8. After that it will become 9. So 9 is 1, 0, 0, 1. After that it will become 1, 0, 1, 0. This is equal to 10, and it will go on. It will count 11, 12, 15, 16 normally. But what I will do now, I will check this condition that this output is equal to 10 or not. Okay, so output equal to 10 means Q3 is equal to 1, Q2 equal to 0, Q1 equal to 1, and Q0 equal to 0. So this is this point. Okay, so we will do this. We will check when output becomes 10, which means 1, 0, 1, 0, right? 1, 0, 1, 0, and then we will reset all flip-flops to 0. How? So let me do it like this. Okay, so this is Q. Okay, so I will have a logic circuit which is like so Q3 equal to 1, Q3 should be 1, Q0 should be 0. So let me put a inverter, and then I take this out. Then this should be Q1 is 1, so okay, and let me take a 4 input AND gate, connect all this. You can take 2 input AND gates also, and 2 signals at a time, then other 2 at a time, and then the result of them together. That's also fine. So but because I do not have space, so I'm taking a 4 input AND gate. So this function is therefore, if you call this call it y. Okay, then this y is same as what? It is same as q3, q2 bar, q1, q0 bar. This is y. And now what we will do, we will connect this y to this reset. These are the outputs. Okay, so these are the outputs, and from which I take this, take them, combine them, and connect to reset. So what happens? The moment, okay, so the moment these four values go to this 1010 level, okay, the moment that happens, then this y will become 1. So at this, if I write y, also y, so y will become, y is 0 here, 0 here, 0 here, everywhere it is 0, but at this moment y is 1. Now y is connected to reset, so this is same as reset. So at this moment, immediately reset will be activated and all these values will become 0. So they will go directly from here to here. So they will take almost no time from, to go from here to here. So the moment it comes from 9 to 10, immediately it goes to 0. Okay. So as these clocks are coming here one by one, after first clock, the number goes from 0 to 1, then 1 to 2, 2 to 3, so on, then 7 to 8, 8 to 9, 9 to 10, and immediately to 0. Okay. So then this step doesn't exist. It doesn't, it exists for a very, very negligible amount of time, and it doesn't also count these clock pulses, because the clock pulse which cause the counter to go from 9 to 10, at that same clock pulse only, it has gone from 10 to 0. So no extra clock pulse is required to go from 10 to 0. Okay, so that's why this arrangement will now circulate between these states 0 to 9. 10 is a almost non-existing state. Okay, so this circulates from 0 to 9 and so on, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0, so on. So this is a decade counter. Okay, so we have realized our decade counter. So we will talk about another topic now, which should also be useful for making digital instruments. So this is a display. This is a display unit. We call it a 7-segment display. You all have possibly seen it. So this is basically a set of 7 LED or LCD, okay, or 7 lights arranged in this way. Okay, so this is one light, this is another light, okay, this is another light, this is another light, another, another, another. How many do we have? 1, 2, 3, 4, 5, 6, 7. Okay, so this looks like a 8, number 8, right? So this is called a 7-segment display. Now this can be LED lights, and let me just give them some names. A, B, C, D, E, F, G. Okay, so these are some lights. Now we can turn on and off these lights to generate or display different numbers starting from 1 to 9, 0 to 9. How? Say if I just So for example, if I turn this light off, then okay, this looks like 0. Now similarly, if I say turn this 2 off, okay, so these 2 are off. Now it looks like 3. If similarly say I can turn say this one off, and then it will look like 6. Okay, so by turning on and off these lights, this is 8, I can generate or display any number from 0 to 9. And now these are LEDs. Okay, these are all LEDs, light emitting diode. So how can we? So let me draw a circuit diagram of these diodes. So I have said these 7 diodes. So let me draw these 7 diodes. 1, 2, 3, 4, 5, 6, 7. Okay, say these are so all this upper side is the positive side. Say I connect them all together. Okay, so this is the anode side. This is called common anode connection. Common means all anodes are connected together. All the positive sides are connected together. And say I connect this to 5 volt, some voltage. Okay, and on the other side I connect some resistances, some suitable resistance, and I have a switch. And after this switch, this side, so which is this anode side, negative side, they are all connected to 0 volt. Okay, so now what happens if I say connect this switch, then this LED will glow. If I connect this switch, then this LED will glow. Similarly, by connecting these switches, I can choose which LEDs to glow and which to not. So call this as A, B, C, D, E, F, G. A, B, C, D, E, F, G. So if I, and these are all so these are electronic switches. They can be transistor. Okay, so they are not manually operated switches. They are transistors or some electronically operated switches, although I'm drawing them like this symbolically. Okay, so by choosing which diodes to turn on, say if I choose for example if I connect say B and C, okay, suppose if I connect B and C like this, okay, all others are off, only B and C are on, then only this 2, okay, this 2 will glow, and this will be equivalent to binary 1, sorry, decimal 1, this display 1. Okay, so this way we can generate any decimal number 0 to 9. Okay, we could also have a small variation like this, where instead of having the switches on this side, we could also have switches on the other side. Okay, so let me just join them and put switches on this side here. So this is called now common cathode connection. Okay, so this is also possible. And if you are to calculate these resistances, basically then you need to know that how much current should pass through these diodes so that they are properly bright, they are glowing properly. Then you can divide this applied voltage with the required current to compute this required resistances. Okay, so if you are asked to design a circuit and compute these resistances, required resistances, where you know that the current that should flow, which says I ampere, or maybe it's not ampere, it's maybe milliampere or less. Okay, and then if you know this voltage is 5 volt, then divide 5 volt by I to get what should be the resistance that is to be connected in this circuit. Okay, so this is 7 segment display. Now, so we have seen two things. We have seen decimal decade counter, okay, which is here. This is a decade counter. Okay, we have seen how it works. Now let me draw the decade counter in a simplified way like this. So it will have 4 outputs definitely. Q0, Q0, 1, 2, and 3. These are the 4 outputs. So let me draw these 4 outputs or flip-flops just like this for simplicity. Q0, Q1, Q2, Q3. So these are the 4 outputs. So this is a decade counter or decimal counter. Okay, and it has a input. What is that input? It is this clock pulses. Okay, so I should draw the input. So let me draw the input here. So this is the input, or you can call it the clock. I should put a triangle to denote the fact that this counter is sensitive to edges. Okay, so that means the counter counts or changes its value only when a edge comes. And I can also draw a bubble if it is a negative edge triggered counter like this. This was a negative edge triggered counter, but by putting say a NOT gate here, I can also make it positive edge triggered. So depending on which type of counter I use, I put a bubble or not. So this is the symbol of a decade counter that I will use. Then after this we have seen this 7 segment display. Okay, so and it will have so let me put this in a box. It will have 7 inputs: 1, 2, 3, 4, 5, 6, 7. A, B, C, D, E, F, G. What are these inputs? These inputs are the states of these switches. Okay, so depending on what voltage this box receives, A, B, C, D, E, F, G, these switches here will be either on or off. Okay, that's what I mean in this diagram. So it has 7 inputs, and accordingly the display will take a form: 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we will put a box which we will call a 7-segment display driver. Okay, so it has 4 inputs which will connect to this output of the decade counter. So these are the outputs of this decade counter, and these are the inputs of this 7-segment display driver, and it will have 7 outputs, and these outputs will connect to this 7 inputs of the 7-segment display, LED display. So these are outputs. What is the function of this driver? The function of this driver is to see or watch these 4 values, understand what is the decimal equivalent of these 4 values. Say if these 4 values are like, for example, 0, 1, 0, 0. So this is like binary 4, right? So that means the counter is at state or count value 4. So the function of this driver is to set these 7 outputs in such a way that so that these LEDs show the number 4. Okay, so when is that possible? So to set the number 4, I have to say turn this one on, this one on. Okay, so let me draw it this way. So to make it 4, I have to make it like this. Okay, so that means F, B, G and C. F, B, G and C will be on. So F, this will be 1, B, this will be 1, G will be 1 and C will be 1. Remaining things A, E, D will be 0. A, D, E all are 0. So the function of this 7-segment display is to create these outputs so that this number is displayed here. Okay. So if I write that it watches or sees the binary number coming from the counter, and decides which LEDs to turn on or off. This is its function. So how will it work? This is nothing but a logical circuit. This is just a digital logical circuit made up of AND or NOR gates, so on, nothing else. Okay, so how can we design it? So we can design it like this. So we have to make a truth table, then do some binary function simplification using Boolean algebra or Carnot map, whichever you are familiar with, whichever you are comfortable with. Okay, so let me just tell you that very briefly. Okay, so so for the 7-segment display, so let me write the truth table. So it has 4 inputs, Q3, Q2, Q1, Q0, 7 outputs, A, B, C, D, E, F, G. Okay. So now if these are like 0 0 0 0, this is same as decimal 0, then if so, we know to sort 0, we have to make A, B, C, D, E and F on G off. So 1 1 1 1 1 1 0. G will be off, everything else on. Now then, if this is 0 0 0 1, so this is like binary decimal 1, then we should make B and C 1 1 1, everything else 0 0 0 0 0. Let's take another value, then 0 0 1 0, this is like 2. To display 2, I need A, B, G, E, D. A, B, G, E, D. Okay, so let me put A, B, G, E, D, 1, everything else, which is C and F equal to 0. And this way you can fill up the table. Okay, so I just put it as a small homework. Please complete the table. Complete the table and then simplify the Boolean functions using Carnot's map or whatever method you like, and then realize a digital circuit with AND or NOT gate, and realize a digital circuit. Okay, so since this course is not really on digital electronics, so we are not going into further detail. You can do this yourself, I believe you all can do it. This is very simple. Okay, so this is about 7-segment display. Okay, that's it. So this is the end of the first chapter, which was on the background required from digital electronics. And next day we will start with analog electronics, op amps. Okay, thank you.